So today we're going to be taking a look at a few quick examples of reduction and reductive proofs. That is to say, how do you take a certain Turing machine and prove that it is undecidable using a pre-existing known undecidable Turing machine. So for example, for both of these examples that I'm going to be using in today's video, we're going to start by knowing that the Turing machine for the halting problem is undecidable. Now, if you're not familiar with the halting problem, essentially what it says is that when given a machine M and an input W, there's no way to know whether or not M halts on W for all cases. That is what the halting problem says at its core. And we know this already to be unsolvable. So we're going to use the halting problem to solve the question, does M halt on the empty tape? So I have this box here with two smaller boxes, and I'll get to those in a second. But at the core of this, and I hope this diagram can really clear things up, is this outside box is the Turing machine for the halting problem. And inside, we have the Turing machine for halting on empty. Now, this is a decider function, so it's going to tell if a certain machine M halts or does not halt. And in effect, what we're doing here is we're going to use this problem, the Turing machine for halt on empty, to solve the halting problem. And if we can show, if we can do this, then we know that this machine can't exist because it's solving an unsolvable problem. So let's take a look first at this function, halt on empty. And let's take a brush here, and we know that this function is going to return either yes, the machine does halt, or no, the machine does not halt. And this is going to be true for all cases, which means that this machine, we're assuming that this machine is decidable. We know it's not, but in order to prove that it's not, we have to start by assuming that it is. And we're going to be passing a machine here, M sub W, and I'll explain that in a second. But we're simply going to say if M sub W halts, then yes. Otherwise, say no. That's all this function is going to do. And this right here, if M sub W halts, we don't need to know what this does. We don't care. We're assuming that it can. We're assuming it exists. But let's talk about now this function, or this machine M sub W. What is it? How do you build it? And what does it have to do with either of these Turing machines? Well, we know that since this outer box is the Turing machine for the halting problem, we know that that machine receives as input an M, and we know it receives a W. Some M and some input W. It'll run W on M, and it will tell us if M halts or does not halt. So what we're doing here is we're going to build a separate machine that will be solved by this one, or by the halt on empty, rather than the halting problem itself. So you'll see here what I'm doing in a second, but we're going to call this function t of x, and what we're going to do is we're going to build M sub W. We're going to do this in a few ways. The first thing that we're going to do is we're going to, for each input, write input to tape. So if W is, or well, I should specify, for each input in W, write that input to tape. Then what we're going to want to do is move to left end marker, and then we're going to want to run M. And this is our new machine called M sub W. Right here. So what M sub W is going to do is it's going to take all the input in W, write it to the tape, move to the left-hand marker, and then run M. So as you can see here, this M sub W is essentially doing the same thing that the halting problem would do. It's taking M and it's running it on W. And if M sub W halts, then we say yes, otherwise no. But what you notice here is that, well, since this is doing the exact same thing as the halting problem, if this says yes or no, or if it's capable of saying yes or no, then this is actually solving the halting problem. It's allowing you to say yes, this machine halts, or no, it does not halt. But we already know that the halting problem is undecidable. And there was nothing invalid about what we did to build M sub W. Writing input to a tape, that's valid. Moving to the left M marker, that's valid. Running a Turing machine, those are all valid things that you can do from within a Turing machine. But since we haven't done anything wrong here, the only conclusion is that, well, this machine, Turing machine for halting and empty, can't exist. Conceptually, I think a big mistake here that you can make is assuming that W is input to M sub W. It is not. W is only input to the Turing machine for the halting problem. We build M sub W by writing W on the tape, but it's not the input to M sub W. M sub W has no input. Remember, we're working on the empty tape. That is the question at hand. Does M halt on the empty tape? Not does M halt on W. That's the halting problem, and that's what we're trying to reduce this problem to. So think of this as more of the rules and less of this is input, because ultimately this isn't the Turing machine for halting on empty. It does not ask for any input. It asks for M, some Turing machine M, and we're giving it that in the form of M sub W. Now, I've written this other arrow here to demonstrate that in reality, it's actually technically passing the empty tape as well. M sub W is being run on the empty tape. So if this were something else, then it would be passed, say it was W as well, it would be passed through this arrow to this Turing machine. But for these purposes, we don't need it because the tape is empty. So now we're going to take a look at a slightly more complicated problem. Given a machine M, a state Q, and an input string W, does M reach state Q from its starting state? And the diagram is a little bit more organized this time, but the concept is the exact same. We're going to use the halting problem, and we're going to reduce this machine MQW to the halting problem, and by doing so, we're going to prove that this machine MQW is undecidable because it solves the halting problem. Now, at face value, this doesn't really look like something that can be reduced down to the halting problem, but as you'll see in a second, it is. So again, this outer box is the halting problem, the Turing machine for the halting problem. This machine T of X is the, it builds this machine M prime. M prime, the input and the state Q is passed to this Turing machine up here. And if M prime halts, then we say yes, otherwise we say no. And again, we don't care what this function is doing. I know that's it seems like a simplification, but it's really irrelevant to the problem, what this M prime halts does. All we need to know is that it works. We're assuming that it works. So how do we build this machine M prime? And again, we have as inputs a machine M and a string W. So now let's build this M prime. And a quick qualification that I should make here is that we're going to let Q be equal to the halting states of M, which means that in here we could say some H is equal to Q, meaning that for every halting state in M, that is all now going to transition to this one consolidated state Q. So if M had 5 final states, M prime has state H. That is it. So we're adding a state and we're mapping all the final states in M to this H. And now all we want to do is, again, let's create transitions from, I should probably put this in parentheses because we already defined this, but let's say it again. Create transitions from final states in M to H. And finally, we're going to run M on W. So those are the 3 things we're going to do. Much simpler than it looks like it might be, but effectively what we've done here is that for every time that M halts on a string, now M prime will halt. So to clarify this, let's go in here. We're going to pass to this M prime, we're going to pass to this W, and we're going to pass to this H. And now if M prime halts on W, then we say yes, and if it doesn't, then we say no. But what do you notice here? Again, building M prime and saying that H is equal to all of the final states in M, we've turned the termination of M, or rather the halting of M, into a black or white matter. Yes or no. Halts or does not halt. And in doing so, we're doing exactly the same thing as the halting problem. If m prime halts, that means that it has reached state h. If it does not halt, I mean it hasn't reached state h. But that's the same as saying if m reached its final states, then m halts, and if m did not reach its final states, then it does not halt. And it's really that simple. So in that way, we can tell that m prime is equivalent to m. Therefore, MQW solves the halting problem. Therefore, MQW cannot exist.